You want to start again, please?
Okay, yes, I'm trying to share the screen. Okay, perfect. So, as I said, we made a number of measurements, ice melt, etc., hydrology, and so on. Well, I will spare you the hydrological model, but there is some complexity, of course, in. This is a picture from the high-altitude camps of the Gasherbrum, where Christoph Meyer, another fellow, measured snow depth with this radar. So we had some information about snow accumulation also in the high altitude. Well, this is a graphical representation of the type and quantity of data necessary. But anyway, one interesting point I want to touch, and that's why I put this figure, is the behavior of precipitation in altitude. As you can see here in this chart, we have elevation and mean annual rainfall. And these yellow dots are measurement at low altitude, all the way to 3,200 meters, which is low altitude in the Karakoram, of course, maybe not here in Italy. Well, the interesting thing is that everybody is basically hypothesizing or putting forward the fact that precipitation is sort of indefinitely or ever increasing at the high altitude, while in reality we were able to get some snow pits data, and we were able to date them, and we could see that in reality snow accumulation in 1 year is slightly lower than one could have expected, and also other findings have been demonstrating that in reality precipitation is not ever increasing at all altitudes, but at some point there is an inflection and it starts decreasing. This is interesting because if you postulate that precipitation is increasing so much at the very high altitude, you could get paradoxical results, which is ever increasing snow cover and ever increasing glacier, etc., which is probably not the case. This is the grid area, and this map here on the right bottom demonstrates that when there is some debris cover on the ice, we could measure debris cover all the way up to 35 centimeters. This number here, which is the melt of ice in millimeter per day for every Celsius degree, basically decreases. This is called shielding effect or debris cover effect, which means that if you have some debris, some rocks or stone covering the ice, basically the ice melts slower. So this is a sort of shielding or protecting factor on glacier. And many glaciers in the Karakoram area are covered in debris, as you can see here, even with very thick debris pieces and rocks, etc. And this is one possible reason why there was some decrease of the intensity of ice melt in the Karakoram and in other areas with debris cover glaciers. This is this is the output of the model, with the model discharge in red and the observed discharge in blue down at Shigar. But I can draw your attention on this chart here on the right bottom. This is the total discharge model, and the blue part is the contribution from ice melt, which, as you can see, is tremendously high, even in the order of 70 to 80% or more. And in September, we even estimate 90% of contribution from ice melt. We could say that this catchment, which is quite dry and arid in terms of climate, in reality takes a lot of water from ice. The mean annual precipitation over at the low altitude in the catchment may reach 300 to 400 millimeters, which is very little. So in reality, a lot or large contribution to hydrology comes from ice melt. And this is a map, for instance, of ice velocity. You may be surprised that ice glaciers, in reality, glaciers are in reality living bodies. They move very quick, and in some parts of the glacier, where the glacier depth is in the order of 1 kilometer or so it's 1,000 meters of ice, you could have velocities all the way up to 200 or so meters in 1 year. So basically, when you stay on ice, for instance, with the tent or something, in 1 year, you may move by 200 meters or so downstream. So we have other pictures here from the glacier. I just want to say something on the topic of climate projection. You might have heard that the IPCC and other intergovernmental bodies are relying for their politics and their conclusions about the future climate of the Earth, basically are relying upon projection. Projections are made by GCM's model, which is general circulation models, and they provide on a very coarse grid in the order of hundreds of kilometers or so, projection, which is scenarios of the future climate, temperature, precipitation, etc. What we need to do here is to use such a projection to feed hydrological models, which take in input precipitation and temperature and other variables, to see what would happen in the future if the climate would evolve, would change in some way, and how this would affect the hydrology. To do so, we need to make a number of assumptions, the most important one being that we can use the data from the general circulation model, but we have to adapt or tailor this data to the local reality. This thing is called downscaling, and it is very important. And basically what we do is we compare the data from the GCM to data from ground observation. We make a sort of mix of the two, and we come up with projection for the future. And with this projection for the future of the climate, we project for the future even hydrology and the behavior of the hydrological catchments. And this is a typical example, for instance, of the projection of global temperature change. I just linger a little bit on these RCPs here. So we can call RCP 2.6 the best case scenario, which is the blue scenario here. It's called overshoot pathway, maximum temperature half century and then decreasing. And then RCP 8.5, which is the worst case scenarios, all the way up to 4 degrees or so until the end of the century. And this is the fork, the degree of uncertainty in how temperature on the Earth will evolve, depending on the policies from the countries of the world, which is changes in energy mix, environmentally focused policies for use of different type of energy and pollution, etc. So basically, they are called what-if scenario. What would happen if the climate system would evolve in a certain way, namely in terms of concentration of greenhouse gases, CO2 and other equivalents. This is just a representation of downscaling, which is you start with a very coarse grid from a GCM model, and then you come up with a representation at a small scale. This is a catchment in northern Italy, for instance. This is the application to the Karakoram case, and you see we have used 3 models, and each model has a different SWOT on the ground, which is the footprint or the cell of the model, and they include in different ways the region of interest. So by using the outputs of this model downscale, we can assess, for instance, the discharge variation, which is the change in water available in the river. And at half century, we have increased, and you see different scenarios from the, let's say, most optimistic one to the most pessimistic one, and different model. These are all different models or GCM's models. ECRT is European, ECAM6 is German. Not that German is not European, of course, but ECRT is an integrated model from different European countries. CCSM is American, basically, from Boulder in Colorado. They all agree in increasing discharge at half century, but at the end of century, some of them indicate decrease of available flow. What's the reason for that? Well, first of all, the hydrology of the river would change. Here you have the historical dynamics of the stream flows during 1980-2012, which is the dashed line here, and you have changes in the future discharges in different colors, indicating mostly a shift towards left, which is faster melt, and then a decrease towards the end, meaning less water available under ice melt and snow melt. This is the waiting season. You should know that in fact, during this period, you can reach the Concordia region and make also climbings in the many mountains, in the many peaks of of the place during this season because you can wade rivers. And you can wade rivers in this way here. Well, in reality, in the future, if the discharge would become larger, you should find other ways to reach the base camps and the summit because water would be very high. Well, this is interesting. In fact, what you see in this picture, ice volume at 2095, which is projected ice volume at the end of the century in the different altitude belts. This dashed line black here is the estimated amount of ice now. And these different colors, from the most optimistic in red, in green, to the least optimistic in red, is the projected decrease of ice volume in any altitude belt. And this chart here is let's say a different representation, which is the amount of glacier melt in years. And you can see that starting from 2010, you would have an increase according to all scenarios, and even an increase according to scenarios RCP 8.5 in the second half of the century. RCP 8.5 again is the most pessimistic one, but eventually, after some point in the century, you will have decrease of ice melt. What does it mean? Well, it means that ice will be retired, less volume of ice, less ice melt, and less contribution to the stream flows. So basically, this area with a arid or semi-arid climate would even decrease largely or even lose the contribution given by ice melt. Well, I'm not going to show this, but you can even predict, according to different scenarios, the ice depth along the centuries. And you can have slight changes of it. Well, I can show it very quickly. As you can see, along the century, along the century, you will start from some depth, 2035, yellow, meaning 600 or more. And then you can go forward in time all the way to the end of the century with very rapid down wasting of the ice and decrease of depth in the order of 300 meters or so. This is the worst case scenario again, but in reality, temperature right now and even the evolution of ice bodies worldwide, including the Arctic, for instance, is going, well, as fast as we expect according to the worst case scenario. So this is not totally unlikely or not totally impossible, you could say. What I want to show you is that these traits are basically common in several areas worldwide. We also made some studies and some investigation in other catchments. One of these is the Dudh-Kosi Basin in Nepal. I think Michele has been there for some studies. I don't know, maybe Danilo also, under the framework of this cooperation with EK2CNR. It's a relatively well-studied areas, again, because there are many scientists from many places worldwide studying this area. And we studied hydrology of the highest part of the catchment. This is called Dudh-Kosi Glacier, which means the glacier of, the river of milk or milk river, because it's very whitish color. And Everest summit is here, and this is the very famous Khumbu Glacier. And basically the ice fall, the very famous ice fall, starting from which you can walk and go all over the Everest. So it's this piece of ice cascade just upstream the base camp is here. We have done some studies. We have measured the stream flows. Well, this is the very famous Everest K2CNR pyramid at the toe of the Khumbu Glacier. In reality, this is the Lobuche Glacier, and this is the Mount Pumori. Here you have some picture. This is Namche Bazaar. This is Lobuche, and this is the Changri-Nup Glacier, which is the west part of the Khumbu Glacier. Well, we studied basically the hydrology of the river. Our measuring station is here at the outlet of the catchment in the Perice place. This is at 4,200 meters or so. We could use data of an hydrometric station which was installed basically by the the CNR of Brugherio. So I should thank here Franco Salerno for delivering this data, and we basically calibrated the station with flow measurements, etc., and we could come up with this estimated stream flow here, and then we could use a model. So QOBS is the black one, which is the value of discharge that we could measure from the station, and then we could model. Well, it's in red or green, same thing, and we could model quite well actually the discharge coming out of the catchments. And you can see here the contribution on the left bottom, the contribution of ice melt, which in some months reaches 68 or more share. Again, meaning that here a very large part of the stream flows is related basically to ice melting. Again, here we are in a very altitude area. As I said, the temperature is 4,200 meters. Shigara instead is lower, is 2,000 meters or so. But anyway, even depending on altitude, still the contribution of ice melt is very important. We did some studies also in Chilean catchment, which is in the southern in the South America. For instance, this catchment here is called the Maipo River and is feeding the city of Santiago del Chile. During this project, where also Danilo participated in 2012, in reality. We made some local assessment, and we made some projection, etc. And we projected future discharges and future ice extent. Here it's also an Italian case, which is called Malero River. It's in the northern part of Italy, and there are a lot of glacier within the catchment from the Bernina and Disgrazia group. And here you can see these glaciers mapped. Again, here we made some field activities, some modeling, etc. Here, for instance, we use an interesting technique, which is we quantified the ice melt from different digital elevation models in 2 different periods, from 1981 to 2007. And here you can see the amount of ice melt in that period, all the way up to minus 70 meters in this part here particularly, but also here in this area in the west, meaning that in less than 30 years, these glaciers may have lost all the way down to 70 meters or so, which is 2 or more meters of ice waste, ice melt in 1 year. Then we made a projection for the future, and you can see here in the map the worst case scenario, which is the green map, and the best case scenario, which is the blue map, compared with the ice depth right now, which is, sorry, 1981, the red one. You can see that the future scenarios seem very, well, inclement, I would say. Here, in the right bottom part, you could see the projected stream flows for every month in the same catchment. The black dashed line is the present, and of course, the color line are different scenarios for the future for the same month. Especially in July, well, June, July, August, even September, you would see much less water available. On the bottom part, you have half century, and the top part, upside down, you have the end of century. At the end of century, many scenarios will give 50% or so of the water available now, meaning a very large decrease of water available during summer, which is snow melt and ice melt. Some increase, as I said, in fall, and some increase even in winter, but notable increase in fall, meaning more liquid precipitation in fall with more availability or proneness to fall floods. Again, given by basically the uplifting of the thermal zero, so less snow precipitation, more liquid precipitation, and more floods potential. This is the ice contribution. Terribly, terribly decreased, in fact. Common traits are raising. So, projection of the future amount of ice water equivalent, which is basically the volume of ice stored in the mountain for these catchments. This is again the Malero River, so Italian Alps, This is the decrease between 1980 and 2000. And this is the projected future decrease, ranging from, well, slight decrease, most, let's say, best case scenario, all the way down to 0, worst case scenario. Similarly, in the Maipo River, from a slight decrease to very large decrease, similarly in the Mount Everest. These are observations we could make. In fact, well, I think this was mapped with satellites. Slight to large decrease. Well, we go back to Karakorum. Is there an anomaly thereby? Well, in our simulation from 1980, we could, in fact, provide some chance for slight increase or stability in the last 20 years or so, which would partly motivate which would partly substantiate the hypothesis of stability. However, as we will proceed forward in the century with increasing temperature and probably constant or even decreasing precipitation, but again, the precipitation is very low in this area, as I said, in the order of 200 to 400 millimeter per year, which means very arid area. The lack of ice cover and decrease of ice cover will provide a large decrease of water availability. So, well, I don't know what happened here. Well, here, namely, we have an anomaly, but in reality, we expect that in the future, this anomaly will be offset by the increasing temperature thereby. I want to show this. Well, here we can represent on a chart the nexus basically between precipitation and ice cover, meaning that in catchments that now have a very ice cover, like for instance the Shigar River here, all the way even at the end of the century, this is an intermediate scenario. It is called 4.5. So not best case, not worst case. So for different scenarios, we may have different situations. However, in catchments with larger ice share now, at the end of the century, you may still have some increase of water availability, but under the best, well, intermediate case scenarios. In situation where you don't have very much ice cover, but you have still constant precipitation or so, you may have slightly increased amount of water. However, in situation where you have a large decrease of precipitation, so you can read here from delta P negative, so lack of precipitation, the amount of delta Q, which is the change in available discharge, would be very large. And instead, on the right part, if you have large amount of precipitation, which is increasing precipitation, increasing discharge availability. So what is the bring home message here? Well, if in the future, in such catchments in the temperate regions with some ice contribution, if in the future more precipitation will be available, possibly we will have more water, more discharge. If less precipitation will be available, we will have less discharge. The effect of ice will basically be offset, which is on the long term, the ice will disappear and these regions will be entirely or more largely dependent on precipitation. Unless for a situation with very large ice cover, where even until the end of the century, you may be able to have again more water or a constant amount of water, but at the cost of melting the ice. So maybe the problem will not be shifted until the end of this century, but will be shifted forward in time. But still, ice cover will be largely depleted. Well, something about the expected fallouts, because as I said, this may be an interesting stuff, maybe, or a mind game even for hydrologists, but may not have large practical impacts. Well, a number of expected fallouts can be envisioned or forecast in reality. And well, you see here in black some of the possible fallouts, and I will rapidly think about hydropower production and river habitat and temperature. Well, about water distribution in chemistry, For instance, Michele knows better because we did some investigation, for instance, on the chemistry of the water related to glacial stream, etc. This is also interesting. Well, as I said, floods and droughts. This is a very complex, of course, item, and really depending on the location and site, etc. But as I said, generally we expect less water during summer, more water during winter and fall, so possibly more floods. Again, this is a very complicated topic, even because the statistics, let's say, in order to investigate such facets, let's say, in a scientific, viable, and correct way, you need to use statistical tools, and statistics requires information and data, etc. So when you talk about floods and extreme events of precipitation, etc., you need complex statistical tools. So it's a very complex topic. Oh, soil erosion, for instance, if you want to see on the internet, we have this E-Raise project, which was really was a funded project from the Cariplo Foundation of Lombardia region, where we work it, and this was related to the impact of climate change on soil erosion in the mountains. This could be also of interest. I will talk now a little bit about hydropower production, and then I will say something very quickly about temperatures and river habitat, meaning water temperatures. Well, why is the point with hydropower of interest? Well, here we have a picture, basically, of northern Lombardia region, divided in two different regions, R1 and R2, basically two regions where you have different regime of precipitation. In region R2, there is less precipitation in the year and in the winter, so less snow amount. But this is not very important. The important thing is that you have these blue fields here, and this is ice cover, and these yellow dots are all hydropower plants. Well, intuitively, you can immediately see that hydropower plants are in the high altitude, and oftentimes they are just downstream of glaciers. Even if they are not downstream for glacier, it is still plausible, it is still possible that downstream the glacier there are artificial canals or artificial ducts, pipes that take the water from the glacier and they move it, they carry all the way to the hydropower stations. And so in this hydropower station, you pump, better, you turbine, which is used for production of energy, water which is coming from some melting glacier or snow and ice covered area, even though the power plant is not physically downstream the glacier. So it is also complicated to reconstruct this complex structure of the hydropower production system, because in reality you get water from somewhere, you move it elsewhere, and then you use it. But anyway, we were able to make some calculation, and as you can see in this picture here, sorry, in this chart here, bottom right, we were able to calculate the quantity of the share of water coming from rainfall, snowfall, and ice melt for the production of hydropower. So, for instance, we call this QMI, which is the amount of water coming from ice melt for hydropower production. It's an average of all the hydropower plants in Lombardy region. It depends on the altitude, which is the altitude of the plant, because different hydropower plants are at different altitude. Well, and the interesting thing is that an hydropower plant which is downstream is basically taking water from all the situation upstream, and this water is conveyed, is brought all the way down to the plant. So there is a sort of integral use of the water coming from upstream, okay? Well, in the downstream plants, which is the biggest one with the more hydropower production, you may be able to have all the way up to 20% or so of water used for hydropower production coming from glaciers. And if you consider snow melt, which is the square part here, well, from down to up, you may be able to reach even 45% or so of water coming from snow melt. So basically, snow melt season and ice melt build up all the way to 40 to 60 or so percent of the total available water for hydropower production. So hydropower production exploits a lot of water from the cryosphere, and water from the cryosphere is very important for hydropower production. I'm showing you a case, and I apologize with Michele, and I think maybe Danilo, I think they already saw this presentation here for this specific case, but it is very important, well, very interesting, sorry, in my view. It's a case study of a power plant. It's called Sabbione Dam, Diga del Sabbione. It's a very high altitude dam. I think until a few years ago, it was the highest power plant in Europe, if not worldwide, maybe, at 2460 meters above sea level. And this is called Morasco Lake, or Lago di Morasco. And this is basically used not only for hydropower production. Sorry, La Diga del Sabbione Dam is upstream here, and the water goes down in the Morasco Lake. And the Morasco Lake is basically the regulating lake of the Toce River. It's a very famous river feeding the Maggiore Lake. Yesterday I saw on the internet, you can go there on Facebook or Instagram or other social media. If you Google Toce River or Fiume Toce, you will see this, or Toce Cascade, Cascata del Toce, you will see this impressive picture of the Toce Cascade, of the Toce waterfall, during this flood, so with muddy water, lots of water, and it was very impressive. And in general, the Toce Cascade, the Toce waterfall is a very famous and very nice one. And it is basically regulated by this Morasco Lake. So it's a very nice place also for going there to visit and working. Morasco Lake, it's 1800 meters in altitude. What was the idea here? Was to calculate the amount of hydropower production related to the hydrology of the Sabbione catchment, calculate how much ice and snowfall and snow melt were important, and what will happen in the future, because the glacier is clearly retiring fast. Here we have some maps going back at the end of the 19th century, and here we have an animation starting from 1986 to 2011. You will see here, especially in the right part, the glacier retire quickly. Those are satellite maps. It's not a model. See, in 25 years, more or less, no, sorry, yeah, 25 years or so, you've seen a large retirement, especially in this part, but even in the northern part of the glacier. In 1954, the glacier is dipping into the lake, was dipping into the lake. As you can see now, it's largely retired. Well, the presence of the lake, in fact, might have accelerated the melting. We have a number of tools, so a digital terrain model to calculate the area, contributing, the watershed, etc. And this is exactly the watershed and the lake. We could count on a number of pieces of information from satellites and orthophotos of the present and past situation. Ablation stakes, I think ablation stakes were kindly provided by the SME, which is the Italian Meteorological Association, so by Daniele Cadberro and Luca Mercalli, I think. And GPR transits were provided by Andrea Tamburini, who made, with this GPR radar, an assessment of the ice depth along these transects. And you can see what is like a GPR transect, or the interpretation of the GPR transect, basically over a certain transect, which I think is this blue one. You have basically the ice depth. And ice depth is very important and useful because it helps you in defining initial condition from the situation of the ice and how much ice volume and water volume is available. This is the ice condition. This is upside down, and you can see the depth of ice according to our initial condition, which was for year 2000, all the way up to 100 meters or so. And this was used exactly coming from using the transects. We made an estimation, a 3D spatial estimation of the ice depth in order to have a three-dimensional model of the glaciers. Sorry. Okay. So we made some modeling and estimation and we came up with a certain amount of water coming down from this catchment to the power plant. So all this water could be turbine. There is a vertical jump, if I remember well, of 600 meters. So it's a lot of hydropower production, because as you know, the hydropower production is proportional to discharge Q times delta H, which is the vertical jump. Here, you can easily see the contribution given by ice melt and snow melt, which especially during the summer months and the spring and summer months are very high. Okay, you have an information of evapotranspiration here, and you can see that it is quite low, expressed in cubic meter per second, quite low, but in July and August, you have some amount of evapotranspiration because it's a very high altitude. So this term is important, but not so much important. When you get lower catchments at lower altitude, this becomes more and more important. And there is also some part of rain, but this is less. Well, this ground flow is basically rainfall. It's normally rainfall because when ice melts, basically it flows overland. And here you can have also a pie chart of the same thing. Well, this is basically the behavior of the Sabbione ice glacier, Osendorn, from 20,000 to 2017. Here you can see the daily temperature behavior, and you will see here basically the ice depth changing in time. You will see at some point some shadows appearing here, some points appearing because this was the snow covered amount, but then you will see the ice depth of the glacier changing in time and also the ice area, starting from 2000 to 2007. See, if you look here, you see basically a pulsation, which is the snow amount, but you will see that in time, the surface of the glacier is quickly retiring. And also the ice depth is basically decreasing here. See? In 17 years, as you can see, this is from the model, but the model was also validated with images. You had a very quick retirement in this very short period in reality. Then what we would do, what we did was basically simulation of the future or projection of the future according to worst case scenario here and best case scenario in green. And you see the difference here in the chart below, because you will see the mean temperature, this is divided into trimesters. So each number is representative for 3 months. So in the best case scenario, you have this green pattern with temperature which is more or less constant, which means increasing all the way up to 12th century and then decreasing, which is called overshot pathway. And this would happen if we would respect all of the requirements from the Paris Agreement. So if we were very good in mitigating climate change. The red part instead is the worst case scenario, which is with quick increase of temperature until the end of the century. Well, the worst case scenario, if you look here on the left, at the 12th century, basically no more ice. The best case scenario, beyond the end of the century, some inertia, and still a large decreasing of the ice cover, but not that much. However, you must keep in mind that an increase of 2 degrees is still a very impacting factor upon the dynamics of the glacier. So increase of 2 degrees above the long-term pre-industrial situation still means the retirement of the glacier. It's not a steady condition for the glacier. Available stream flows decreasing in all scenarios. See, all of these bars here point to half century and end of century decrease of water available. Okay, and lower and lower ice contribution at the half century and end of century. Presently, ice contribution is in the order of 10%. Okay, we just go back quickly. 11% something. Okay. Now, so in the future, it would be much less, in the order of 1-2%. Okay, half century and end of century. What about production of hydropower? Well, this is quite complicated. We made models that are a little bit complicated, so I will not linger too much into that. I will not spend time to this. But anyway, we model the demand for hydropower, which is how much hydropower will be requested for anthropic use along the century. This was done on a daily basis using some models which relate hydropower request basically to temperature and to economy by using indexes of economy such as the gross domestic products and others. Then we also model the price of hydropower, and by combination of the amount of water available to the hydropower plant coming from the catchment, so how much water is available, plus demand of hydropower and price, we could calculate the production and revenues. But here I'm showing the production because the revenues are not very representative, because revenues depend on the amount of cost, well, or of the increase of cost of hydropower, but it doesn't say much about production. You can have less production but more revenues because the price will increase. And you can see here, for instance, the increase in mean energy price in the most optimistic to worst case scenario at half century and at end of century. At the end of century, on general, you would have an increase of the mean price of energy in the order of 160%. So now, for instance, if you pay 1 kilowatt hour, like 0.3 euros or 0.2 euros, at that point you would pay 0.4 or 0.3, so 160% more, okay? Which a considerable increase in the revenues, but look at this, during RCP 8.5, the increase of revenues would be, there will be an increase of revenues, but less than in the best case scenarios. Why? Because of production. Even though you have an increase of revenues, there is a worst case where the production is lower, so you have a relatively smaller increase of revenues. What is the dynamic in time of the production? You can see here, the dashed line here gives you, on the top right chart, the dashed black line gives you the production at present, expressed in gigawatt hours. Okay, so it's gigawatt produced times the hours. This is a way to represent energy. This is basically a number in joule or calories, but this is measured, we say gigawatt hour. Gigawatt is 10 to the 9th watt, and a watt is a joule per second. During half century and during the end of century. Well, as you can see in the future, there will be less production according to all of the scenarios during winter and during fall, as you can see here. So October, November, December, and January, February, March. And if you look at the yearly mean, there will be slightly less production than now. However, a lot of water of hydropower demand will be concentrated in summer. Why? Because of the expectedly much warmer summer periods with much higher or visibly higher demand for hydropower production for cooling. So basically, the impact of climate change on the hydropower system would be a decrease of water available during the proper season, because there will be less water during summer due to reduction of snow cover and ice availability for ice melt. And second, a requirement for a large amount of hydropower water during the summers, with less demand during the winters and the falls. Okay. Overall, the changes in energy production would be all the way down to minus 25% or so in the worst case scenarios, because of the disappearance of glaciers and the lack of snow. So basically, hydropower plants in the high altitudes that are exploiting water coming from high altitude catchments will be impacted by the changes in hydrology, which will affect basically the changes in production. And because in the high altitude of the Alps, there are at least, I would say, 250 to 300 big plants for hydropower production, and they make up 60% of all of the hydropower plants or of the large dams of Italy. We're not counting small power plants. There might be many more, but I'm talking big power plants for hydropower production. Well, a lot of these sites will be impacted. But in some countries worldwide, they're even thinking now that in the next 20 or 30 years, production of hydropower where they do it now will not be viable anymore. So they're thinking moving in other places, maybe northern or southern, depending on the on northern or southern hemisphere. That is where there is now more ice available, but going to melt in the future, because in the temperate regions now, ice covers are quickly down wasted, so less water available. We can resume in such a picture, which is a bit complicated, but in any way we can try and explain. Say, for instance, here on the right you have changes in glacier area, which is reduction of the ice area. Here you have the consistent, the related change in precipitation, and here, sorry, in the y-axis on the left, and in the x-axis you have changes in production. So look, for instance, if you want a change in production in the order of -5%, and say, for instance, you have -90% in reduction of the glacier, so very large change, very large decrease of the ice production, of the ice cover, how much offset of rainfall precipitation you would need? If you go up, you can find this number, which is, in terms of precipitation, if you go right, +15%. What does it mean? These are simulations with many different scenarios. What I'm meaning here? I am meaning that if you reduce the glacier area, even down to -100%, which is no more glaciers, you will need, in order to maintain production constant, 15 to 20% more liquid precipitation. So for hydropower purposes, at least for the Sabbione River, but this is quite representative because there are very many plants as such, like the Sabbione River, if you decrease ice cover, the only way to maintain a constant production is if you have a consistent, visible increase of precipitation in the future. So in a sense, we are at the mercy, in the hands of the future weather in terms of liquid precipitation. Lots of people are saying that under climate change, with more moisture in the atmosphere, more precipitation will be seen. But in some places, in reality, slight decrease is being observed. Just a very quick hint, and then I'm finished about. Elena, vai tu? About, sorry, about temperature in rivers. This is a case of a river in northern Italy. It's called the Serio River, and I'm representing here in this chart, referred to 1980-1990, the number of days in a year when you have a high temperature. High temperature in rivers means 50 degrees Celsius. 1980-1990. Now I will show the projection in the future in different decades, and you will see that this change is largely going toward the red color. Again, percentage of day in a year with temperature above 15 degrees Celsius. Okay, end of the century, large number of large pieces of the river, stretches of the river with 30-40, and many with 20-30. I don't want to, again, I don't have time to stick on this a lot, but is anybody talking? But in the future, not only the temperature of the air of the atmosphere will increase, but also the temperature in rivers. And this will be a big problem because ecosystems in rivers require acceptable range of temperatures. Temperature above 15 degrees become very dangerous for a number of reasons. This is a special report from the Eco Bergamo. Well, the title was terrible. Well, Morte Annunciata, expected death of the river. Of course, this was not the intent of the interview, but the title was made by a journalist, of course. However, in many rivers of Italy, temperature is increasing and the ecosystem may be at risk. Okay, I think I'm done. You can read here some conclusion by yourself, and if you have questions, I am available.
Okay, Daniele, thank you very much. So, if you have question for concerning the first or the second part of the lecture, please feel free to ask or to write. And I just like to add a comment or an answer to Daniele. I've been also in Sagarmatha, not with Michele, but with the second part of the expedition. So we were there, but not together.
Okay. Yeah, as you know, there was a lot of activity ongoing with this committee, etc. And I think maybe it will be starting at some point again because there were some problems, but I think that they're trying to arrange some new activity in the area. So we've been dedicating a lot of time to that specific catchment, etc.
Okay, there is a question from Kika. If I understood it correctly, the ice is melting faster in temperate regions. What about the tropical areas such as the tropical Andes?
Yes. Well, in tropical regions, of course, glaciers are melting very fast because of the very high temperatures. Maybe quantitatively at the worldwide scale, the amount of ice in tropical areas is not so very big. However, it can be important for locally. At that latitude anyway, I think ice cover it's at a very high altitude. I know, for instance, the case of Bolivia, which is in the capital of Bolivia, in El Alto neighbor, they took water from this glacier, the Huayna, I think it was called the Huayna Potosi Glacier, and it basically melted away, so they cannot take water from there anymore. Or even the case I show of Santiago in Chile, there are a number of glaciers within this Maipo River, which is serving the city of Santiago. Very famous glaciers such as the San Francisco, Monos de Agua, etc. And also they are melting away very fast, actually. So this is one of the cases where people will need quite soon to go seeking for other water sources to gather water for anthropic use, basically, because they will need to find other places where to retrieve and to gather water, actually.
Okay, thank you, Daniele. Other questions, comments?
Are there hydrologists in the audience, or people with a background in water science or something?
Maybe they are, but maybe they are following the lecture online. So this.
Okay.
Yeah.
Okay, so if there are...
you will have time to think about this. I think I will send a PDF version of this presentation. You can have time to think about it, and then you can still send me an email. I am very available.
Yeah, Daniele, it would be great if you can also, if you have any suggestion concerning other material, we have a Moodle, you know, a repository where we can add. So if you have a suggested paper, other things that you would like to share, we can put everything inside this platform. It's a Moodle platform, so you are welcome.
Okay, there is an additional question.
There is another question. Sorry.
Sorry, from Kika Bradford.
Yeah, do you know what the expected impacts of these trends in the Paramos?
Well, this is very interesting because some years ago, together again with Michele and Daniele, I think we tried to set up this project which was specifically related to the effect of climate change on the Paramo zone. But as far as I know, we couldn't work on it. And in fact, I'm not very expert. So I know about the Paramo ecosystem, etc., but I'm not very expert. Maybe maybe Michele or Danilo knows better. However, it would be a very interesting topic for investigation, actually.
Yeah, it would be great. I'm not so expert to answer to this question, to be honest. But I think we can find some material, no, Daniele, also you. I think that
maybe we can make a research and provide something on the repository about the Paramo stuff. Yeah.
Yeah, concerning Paramos, I'm not an expert too, but last year we have an expert from the Kew Garden in London. So when everybody will be available, will be able, to assess all the teaching materials of IPROMO course, you will find this documentation in the repository. So you will find the answer to this question.
Yeah, one interesting thing is that in my presentation, I of course talk about hydrology, but of course at the level of soil and interaction with vegetation, etc. Of course, it would be very important to study the feedback between climate, hydrology, and vegetation, including the Paramo vegetation. And that's, for instance, a very interesting point. But for instance, hydrology do not know much about vegetation. Maybe scientists of botanics, etc., do not much about hydrology. Soil scientists do not much about botanics, etc. So it's a very interdisciplinary topic. So it would be very interesting topic for investigation.
Yeah, I think, Daniele, if I could add something, I think this is the spirit of the critical zone observatories. This network of this site where we try to apply a general overview of the system, starting from the canopy, going down to the groundwater. I think it's very important, this interdisciplinary approach concerning all the different components of the system, from the vegetation, hydrology. And something is very challenging and difficult, not to let the people together working on the same subject, but I think that the critical zone observatory approach could be really successful. And we are working in Italy on it, but of course, also in other countries. So I think it could be another great suggestion, a way to proceed, also considering the different perspective, especially for mountain.
Yeah.
Maybe Rosa Laura. Rosa Laura, I think we would like to add something. Rosa Laura, please. We can hear you. Yeah.
Can you hear me now?
Yeah.
Okay. I'm a scientist, but I've been working in the Paramos, and I know that they are considered the best the best ecosystem for hydrological catchment. So they are extremely important for the hydrological cycle. What we have seen and what is happening now, as I'm sure all of you from Latin America know very well, is that because of climate change, many communities are now farming and having animals in the Paramos, and this is compacting the Paramos soils, especially because they're using cows that are not, of course, originally from Andes, and cows have a very heavy pose, so they compact the soil. So the water infiltration is now very limited because of the farming, especially when they farm potatoes there, because potatoes have a very negative impact on the water infiltration that compact the soils a lot because of the use of cows. Because traditionally, these were areas where the camels, Lama, Vicuña, Guanaco, etc., were farmed. Some were even wild there. So now, because of the climate change, it's possible to farm in Paramos. Many communities are farming, they're putting potatoes, they're putting cows, and this has a very negative impact. And the fact that Paramos are catching water they were using as they were doing before, it's an impact on the cities that are that were benefiting from the water that was infiltrating in the Paramos area. So now many cities in Ecuador, in Peru, and especially in Ecuador and Peru, I would say, because this is where you have most Paramos, are suffering because of this reduced water availability. But this has caused important political issues between the communities that are living in the Paramos. Some of these communities are relatively new, so they moved to the Paramos in the recent years, and the local and central governments that would like to remove these communities from the Paramos. So it's becoming a very hot political issue in Peru and Ecuador. So this is what I can tell you. It's a very interesting situation. Thank you.
Yes, you look like an expert on it.
Thanks a lot, Rosa Laura. Great contribution.
I think we should organize a project on Paramo. It's a moment.
Okay, so thank you, Rosa Laura. Thank you very much, Daniele. Now,
thank you for the invitation.
Yeah.
Any compliments for this very nice initiative.
Thank you, Daniele. Thanks a lot, Daniele.
Thank you so much. So now I'm
see you
opening
again next time.
Bye. So now I'm opening all the microphones, so we can say thanks to Daniele by clapping our hands, and see you tomorrow for the next IPROMO course.
In the afternoon.
Okay, so the next session, what time starts?
In the afternoon. The next session will be tomorrow in the afternoon.
You're welcome, Daniele. You're welcome.
Yeah, but I have masters today.
I know, but you could be very busy. But in any case, the next
3
day
courses this semester, so I'm quite busy. Okay, bye-bye. Thank you so
Daniele.
much.
Thanks again. Ciao, Rosa Laura. Ciao a tutti.